right now, this specific moment, wherever you are, whatever hour the dark has settled into where you live. A radio signal is moving toward Earth. It left its source yesterday, not in the loose, conversational sense people use when they mean a little while ago. Literally yesterday. Calendar yesterday. Sometime in the last 24 hours. A spacecraft moving at 17 kilometers per second broadcast a thin beam of radio waves in the direction of home. And those waves are now crossing a distance so vast that even light, the fastest thing the universe allows, the absolute ceiling of speed, needs nearly a full day to travel it. By the time that signal reaches the enormous white dish antenna at Goldstone, California, almost 24 hours will have passed since it set out. That is the one-way signal delay for Voyager 1 in 2026, 23 hours and 40 minutes at the speed of light. If you wanted to send a reply, a simple acknowledgement, just a received thank you, another 23 hours and 40 minutes would pass before your words arrived. 47 hours and 20 minutes for a round-trip conversation. And the slowest part is not the composing, not the encoding, not the transmission from the dish in the desert. The slowest part is the crossing, the vast, dark, indifferent crossing of a distance that makes every other distance we use in daily life feel like a step across a room. I want to sit with that for a moment before we go anywhere. Not race past it in the way your brain wants to. Efficient, filing things in labeled boxes, moving on. 25 billion kilometers, filed. 23-hour signal delay, filed. The brain does this because it evolved for survival, not for awe. And very large numbers don't register as awe without a little deliberate attention. So I'm asking for the attention. Tonight, I want the numbers to arrive rather than just be received. Because the fact of Voyager, the actual, physical, happening right now fact of it, is one of the most extraordinary things I can think of to hold while falling asleep. Not a thought experiment, not a hypothetical. Something real, moving through the dark right now, while you grow still. Close your eyes if they haven't already started to drift that way. Feel the surface beneath you, the give of the mattress, the weight of the blanket, the air in the room at whatever temperature it is tonight. Right now, at this specific moment, there are two objects made by human hands that are farther from Earth than any other human-made objects in the history of the species. Voyager 1 and Voyager 2. Both moving, both in interstellar space, beyond the bubble of the sun's influence, beyond the boundary between the solar system and the space between stars. Both still transmitting, still sending their thin, faint signals home after 49 years of continuous flight. We can hear them, just barely, but we can hear them. And that fact alone is worth spending a quiet night with. The transmission power of Voyager 1 is approximately 23 watts. That is comparable to a dim incandescent bulb, the kind that barely illuminates a corner of a small room. 23 watts broadcast across 6 billion kilometers of vacuum, and by the time it arrives at the receiving dish on Earth, that signal carries less energy than a quadrillionth of a watt. To detect something that faint requires antennas 70 meters across, receivers cooled almost to absolute zero to prevent their own thermal noise from drowning out the message, and a level of quiet engineering discipline that doesn't get discussed often enough alongside the glamour of launches and planetary flybys. And every day, it works. The most distant object humanity has ever built is speaking in a whisper across the largest distance. Anything we've ever made has ever crossed, and we are still listening. Here is something that should rearrange your assumptions gently before you fall asleep. Voyager 2 was launched first, not Voyager 1. Voyager 2 left Earth on August 20, 1977. Voyager 1 didn't leave until September 5, 16 days later. If you've always assumed spacecraft are numbered in the order they launch, Voyager corrects that assumption quietly and immediately. The two probes were named not by the sequence of their departure, but by which one would cross the heliopause, the outer boundary of the Sun's influence, first. Voyager 1 had the faster trajectory and would reach that boundary ahead of its companion. So the names face forward, not backward. They describe a destination, not a departure. I find that detail meaningful in a way that takes a breath to articulate. Before those spacecraft had cleared the launch tower, the people who built them were already thinking about the end of the journey. Not the launch, not Jupiter, not Saturn, the heliopause. The boundary with interstellar space. They had the whole arc in mind before the first bolt was tightened. That habit of holding the entire shape of a thing in your imagination before it begins, of naming it for where it is going rather than where it started, feels like the right disposition for work of this scale. You can't aim at the edge of the solar system if you can't picture the edge of the solar system. The people at JPL in the mid-1970s could picture it, and they aimed. Take a moment with 1977, because the year these spacecraft left Earth is not abstract histories. It is a specific, placeable time with a texture to it. The year Voyager launched was the same year Star Wars opened in theaters and became a cultural event that no one had anticipated. It was the year Elvis Presley died in August at 42. The first Apple II personal computers went on sale that spring. There was no internet in any form most people would recognize. There were no cellular phones. Photographs were developed in darkrooms with chemical baths and came back a week later from the pharmacy. And in that year, in that world, a team of engineers at the Jet Propulsion Laboratory in Pasadena, California, built two spacecraft on computing budgets measured in kilobytes, aimed them at the outer solar system with mathematical precision, and launched them in the right order for the trajectory and the wrong order for the numbers. And they have been moving ever since. 49 years. Every second. The reason 1977 was the year, and not some other year, was a window, a specific, non-negotiable, once in 175 years alignment of the outer planets that made the entire mission possible. In 1965, a graduate student named Gary Flandro at JPL was working on trajectories for possible outer planet missions, the kind of careful, painstaking mathematical work that sounds less glamorous than it is. In the calculations, he noticed something. Between approximately 1976 and 1979, Jupiter, Saturn, Uranus, and Neptune would be positioned in a configuration that allowed a single spacecraft to travel from one to the next, using each planet's gravity as an accelerating slingshot. This technique, gravity assist, works because a spacecraft flying close to a moving planet can steal a tiny fraction of that planet's orbital momentum, adding it to the spacecraft's own speed without burning any additional fuel. Each giant planet in the sequence would hand the probe off to the next one, faster. Like a relay race in which every runner is the size of a world, and the baton is a spacecraft the weight of a motorcycle. Without that alignment, the grand tour as designed was impossible. Reaching Neptune in 12 years, which the gravity assist sequence made possible, would have required either an extraordinary amount of fuel or an extraordinary amount of time using any other method. With the alignment, the mission was achievable within a human career, within a mission budget, within the operational lifetime of instruments built with 1970s technology. Flandro understood the window, calculated when it would close, and recognized with some urgency what that meant. This is not a mission that can be scheduled for later. There is no later. There is only the window, and whether you go through it now. The previous time the outer planets had been in this configuration was approximately 1801. Napoleon Bonaparte was consolidating power in France. The United States had 16 states. No one on Earth had ever seen a photograph. The process for making one would not be invented for another 30 years. The concept of a spacecraft was not merely unbuilt. It was genuinely unimaginable to every mind alive, and the next alignment will occur around 2152, 126 years from now. Whether humanity will have the institutional memory, the organizational capacity, the political will, the sheer interested attention to take another grand tour when that window opens, I don't know. But the window will be there. The planets will align because the mathematics requires it. Regardless of whether we show up. Before Voyager, there were Pioneer. This part of the story gets interplayed, and I want to tell it fully because Pioneer's legacy contains something that Voyager later inherited, both an inheritance of inspiration and an inheritance of cautionary lesson. Pioneer 10 launched in March 1972, Pioneer 11 in April 1973. They were the first spacecraft to reach the outer solar system, the first to prove that the asteroid belt between Mars and Jupiter was crossable, the first to fly past Jupiter, the first to fly past Saturn. Pioneer 10's December 1973 Jupiter flyby returned the first close-up images of the gas giant and confirmed that the radiation environment, while intense, was survivable for well-shielded instruments. Pioneer 11 went on to Saturn in September 1979, 6 months before Voyager 1 arrived, adding a second dataset from the ringed planet. Both probes continued outward after their planetary encounters, their RTGs slowly cooling, their signals growing fainter with every passing year. Pioneer 10's last confirmed reception was January 23, 2003, when it was approximately 80 astronomical units from the Sun. Engineers sent a signal. They heard nothing back. The spacecraft was still out there, still moving, still physically intact. It simply no longer had enough power to transmit at levels the receiving antennas could detect from that distance. It went silent. Pioneer 11 had gone silent earlier, in November 1995, at roughly 44 astronomical units. Its power depleted faster because the more intense radiation environment of its Saturn flyby had accelerated the degradation of its systems. Both are still moving still drifting outward through the darkness, still carrying their small gold-anodized aluminum plaques, precursors to the Golden Record, Carl Sagan's first attempt to put a return address on something we sent into forever. But here is the part of the Pioneer story I want to dwell on, because it is one of the most genuinely humbling episodes in the history of physics, and because it matters for understanding how Voyager was designed. For decades after Pioneer 10 and 11 fell silent, scientists analyzing their trajectory data noticed something strange. Both spacecraft were decelerating slightly faster than physics predicted. Not dramatically. The discrepancy was tiny, on the order of 8 billionths of a meter per second, a number so small it is nearly meaningless by human intuition. But it was consistent. It was real. It pointed in a coherent direction, and nothing in the accounting of known forces could explain it. The sun's gravity had been calculated. Radiation pressure from sunlight had been modeled. The gravitational pull of the planets had been accounted for. Everything was in the equations, and there was still this small, persistent, unexplained tug pulling both spacecraft slightly back toward the sun. Physicists called it the Pioneer Anomaly. For more than 30 years, it was one of the genuinely open problems in solar system physics. Proposals were serious. Dark matter concentrated in the inner solar system, a modification to Newton's law of gravitation that only manifests at very small accelerations, a framework called modified Newtonian dynamics. MOND, proposed by Mordechai Milgram in 1983, some entirely unknown force. The anomaly was well measured, reproducible across 2 independent spacecraft, and persistently unexplained. Papers were written, conferences debated it. Some physicists were privately excited. This might be physics beyond the standard model. This might be the first cracks in the framework. Then in 2012, a team led by Slava Torishev at JPL published a paper that solved it. The answer was thermal radiation, the Pioneer spacecraft's plutonium RTGs, the same type of radioactive power sources that Voyager also uses, emit heat. That heat radiates in all directions, but because of the spacecraft's specific geometry and the positioning of the RTGs, slightly more heat radiated away from the sun than toward it. That tiny asymmetric thermal pressure, the physical push of heat photons leaving the spacecraft in one preferred direction, was decelerating both Pioneers by an amount exactly consistent with the anomaly. 30 years of mystery, dozens of theoretical frameworks seriously considered, proposals involving dark matter and modified gravity. The answer: the heat from their own power source was pushing them backward. It was always the heat. I think about the Pioneer Anomaly whenever I want to remember what scientific humility actually means. Not the performative kind, the actual gut-level, career-affecting kind, in which very smart people decades following a clue that leads to a mundane but deeply non-obvious explanation that was in the system all along. The lesson embedded in that episode is, when you are modeling a spacecraft's trajectory in deep space, you must account for every possible source of force, including the thermal radiation from your own instruments. The engineers who designed Voyager's mission trajectory in the years after Pioneer's anomaly became known incorporated this lesson. Voyager's trajectory models account for thermal radiation from the RTGs. The Pioneer Anomaly was not a discovery about the universe. It was a discovery about the necessity of complete accounting, and Voyager benefited from it. September 5, 1977. The specific Tuesday when Voyager 1 left Earth on a Titan IIIE Centaur rocket from Cape Canaveral. The launch was clean, the trajectory correct, and within hours, the spacecraft was in the interplanetary medium, coasting toward Jupiter on the most precisely calculated arc that the engineers could design. The spacecraft weighed approximately 722 kilograms at launch, roughly the weight of a grand piano, or a large black bear, or a small car stripped to its frame. It was not large. The 10-sided bus at its center stood about 47 centimeters tall. A 3.7-meter parabolic dish dominated the structure for the communication link back to Earth that would prove to be the mission's most critical engineering success. Science instruments were mounted on a boom. The 3 RTG power sources, grapefruit-sized spheres of plutonium-238 ceramic, were mounted on a separate boom to reduce their radiation interference with the instruments. The whole assembly had an ungainly, purposeful look, a dish with a metal spider attached, which is almost exactly what it was. The computers on board carried approximately 69.63 kilobytes of memory. This is not a misprint. 69 kilobytes, the size of a small plain text email, a fraction of a single photo taken by your phone. The smartphones in our pockets have hundreds of millions of times more computational capacity than the devices that navigated humanity's first journey to the edge of the solar system. And yet those 69 kilobytes were enough, because the constraints forced a discipline that more capable hardware often makes unnecessary. Every bit had to earn its place. Redundancy had to be built in without waste. Reliability had to be designed for from the ground up. The result is 2 spacecraft that have outlasted every reasonable expectation of their operational lifetimes, running software that has not been meaningfully updated in decades, producing scientific data that no other instrument in history has been in a position to produce. Constraints breed precision. Precision breeds longevity. 69 kilobytes, 49 years. Voyager 1 reached Jupiter on March 5, 1979, and Jupiter began offering surprises within the first images. A navigation engineer named Linda Morabito was examining Voyager photos of Io, Jupiter's innermost large moon, specifically looking for background stars to calculate the spacecraft's position precisely. In one image, she noticed something at Io's limb, a crescent-shaped protrusion rising above the edge of the moon, extending outward into the space above its surface. Her first thought was that it might be a small, uncatalogued moon she hadn't accounted for in her star map. She checked the catalog. No moon should be there. She looked again at the protrusion. It was emerging from a specific point on Io's surface, not orbiting above it, but erupting from it. A volcanic plume, active and ongoing, rising several hundred kilometers above the moon's surface and spreading into a crescent-shaped umbrella visible from hundreds of thousands of kilometers away. The first active volcano ever discovered beyond Earth. Morabito had found it while doing navigation math, while looking for background stars, while explicitly not looking for volcanoes. She almost moved on. The shape was anomalous, but the mind, when focused on a specific task, resists detours. She had the presence of mind to stop and ask, "What is that?" That question, followed through, was the discovery. Io's volcanism is driven by tidal forces. Jupiter's enormous gravity flexes and squeezes Io as it orbits, with gravitational stress from Jupiter and from Io's orbital resonance, with Europa and Ganymede constantly kneading the moon's interior, generating friction, generating heat, keeping the inside permanently molten. Io is the most volcanically active body in the solar system. We had suspected that tidal heating might be significant before Voyager arrived. We had not anticipated this. Europa, the next large moon outward, showed something different, and in some ways even more consequential. Its surface was covered in ice, and that ice was crisscrossed with linear features, pressure ridges, dark reddish streaks, and regions where the surface appeared to have broken apart and refrozen in new configurations. Exactly the patterns that form when a liquid ocean beneath an ice cap shifts and moves, cracking the frozen surface above it. If that liquid was water, if the ocean was real, and if the seafloor had chemical energy from hydrothermal activity driven by the same tidal forces heating Io, then Europa might have conditions compatible with life. Not life in the warm, sunlit sense that Earth has, but life in the deeper, more minimal sense of the word. Chemistry capable of self-sustaining complexity. We had been searching for life only in places lit by stars. Europa said the search needed to widen considerably. The Europa Clipper spacecraft, launched in October 2024, is currently traveling toward Jupiter to study this question in detail, arriving around 2030. Voyager also discovered that Jupiter has rings, faint, nearly invisible from Earth, detectable only in specific backlit geometry that the spacecraft happened to achieve at the right angle. Jupiter has rings. Saturn was not unique. Later missions would confirm rings around Uranus and Neptune as well. Every giant planet in our solar system is a ringed planet. We only learned this because something went there. Saturn arrived in November 1980, and the images are still, more than 4 decades later, among the most beautiful photographs any spacecraft has returned. The ring system was vastly more complex than models had predicted. Thousands of individual ringlets, braids and gaps and wave patterns and regions of compression and expansion, driven by the gravitational influence of small shepherd moons orbiting near the ring edges. Saturn's North Pole wore a persistent hexagonal storm, a 6-sided atmospheric pattern the size of Earth, maintained by polar winds, geometrically precise in a way that should not be as surprising as it always is. The mathematics of fluid dynamics permits hexagonal storm structures. Knowing that, and seeing it on another world in amber and gold, are different experiences. And then the choice. Titan, Saturn's largest moon, draped in a thick nitrogen atmosphere with photochemical haze that blocked the surface from view, had been an obsession in planetary science for decades. The atmospheric chemistry appeared complex. Some analyses from Earth suggested organic molecules, chemistry that might be relevant to the question of how life begins. The opportunity to fly very close to Titan was irresistible to the scientists, and Voyager 1 made the close flyby at approximately 490 kilometers close enough to gather extraordinary data about Titan's atmosphere, its pressure, its temperature profile, its haze layers, and their composition. The data was rich, the flyby was worth it, but the gravity geometry of the Titan encounter bent Voyager 1's trajectory sharply upward, out of the flat disk where the planets orbit, and away from any further planetary targets. Voyager 1 would never fly past Uranus or Neptune. That path was closed. From November 1980 onward, the spacecraft pointed outward and upward, above the plane of the solar system, on the express route toward the heliopause. It has not deviated from that route since. Voyager 2, on its longer arc, carried the planetary mission forward. Uranus in January 1986, Neptune in August 1989. The only close flyby those worlds have ever received. The only close look we have taken. Everything we know about the detailed structure of Uranus and Neptune's systems comes from those few days in 1986 and 1989, when a spacecraft built in the 1970s swept through them. We have not been back, one visit each 40 years ago. For most of the 1980s, Voyager 1 flew with its cameras dormant. There were no more planetary targets, no close objects worth photographing. The instruments continued. The plasma detector, the magnetometer, the cosmic ray counter, the instruments suited to measuring what the outer solar system is actually made of between the planets. But the cameras were off. For nearly a decade, Voyager 1 moved through a space that had never been instrumented, listening to things no sensor had ever been close enough to hear. Carl Sagan changed that. Sagan had been part of the Voyager imaging team from the beginning, and in the mid-1980s he began lobbying NASA to turn the cameras back on one last time. Not for new science. There was no scientific justification for photographing known planets from a novel angle. For the portrait, he wanted a family photograph of the solar system, taken from the outside, from the vantage of something that had actually left the neighborhood. NASA said no, repeatedly, and with reasonable arguments. The cameras were dormant. The power was needed for instruments. The planets would be dim from that distance and scientifically uninteresting. He kept asking, patiently, persistently, with the specific tenacity of someone who knows they are right about something important. Permission came eventually. On February 14, 1990, Valentine's Day, which I don't think Sagan chose by accident, mission controllers sent commands to Voyager 1. Now at 40.5 astronomical units from the Sun, just over 6 billion kilometers away, the cameras turned on. 60 frames were captured, sweeping through the inner solar system. 6 of the 9 then recognized planets were visible in the images, and in one frame, in a band of sunlight scattered across the camera's field of view by its own optics, an accidental rainbow of instrument artifacts. There was a tiny pale smear of blue-white. Earth, 0.12 pixels, not 1 pixel, a fraction of 1 pixel. A mote of light that was the combined photons of every human being who had ever lived, every civilization that had ever risen and fallen, every ocean and mountain and forest and city, compressed by 6 billion kilometers of distance into something that barely registered on the sensor. Carl Sagan wrote about that image 4 years later, and I have read those words many times without them losing their weight. He wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. He wrote about our planet as a lonely speck in the great enveloping cosmic dark, about the absence of any hint from the universe that help will come from elsewhere to save us from ourselves, about our responsibility to deal more kindly with one another, to preserve and cherish the only home we've ever known. He died in December 1996 at 62. The pale blue dot remains exactly what he said it was. The cameras were turned off after the session. No more power to spare, no more justification. The last thing Voyager 1 looked back at was home. Then it turned and kept going. Before we follow Voyager further into the dark, I want to tell you what it's carrying. This is the part of the story that changes most in the telling, that shifts from engineering achievement to something closer to a love story, if you give it enough quiet space. Each Voyager carries a golden record, a 12-inch gold-plated copper disc, encoded with sounds, images, music, and greetings, intended for whatever intelligence might one day find it. The question the record tries to answer is the most ambitious question a group of people has ever tried to answer in a practical sense. If we had one chance to tell complete strangers what we are, what would we say? The production was led by Carl Sagan and a team that included the astronomer Frank Drake, the artist John Lomberg, the journalist Timothy Ferris, and a woman named Anne Druyan, who served as creative director. Druyan approached the record not as a highlight reel, but as an honest portrait. What humanity actually sounds and feels like, across cultures and centuries and moods, not merely at its most impressive, but at its most human. The result reflects that commitment. It is genuinely diverse in a way that was unusual for official government projects in 1977, and it is genuinely honest in ways that the people who made it had to argue for. During production, something happened that Anne Druyan has spoken about in many interviews over the decades, and it does not lose its weight when you hear it described carefully. She and Carl Sagan had known each other professionally for several years. In the spring of 1977, during the record's production, they fell in love. She has described the moment of recognition as a long phone call on the night of June 1, 1977, during which they both realized, simultaneously on the telephone, that they were in love with each other. After the phone call ended, her immediate thought was, "I want to put this on the record." Not the phone call itself, what was happening inside her body and her brain. At that moment, she arranged to have her brainwaves recorded for approximately an hour while she deliberately, consciously thought about falling in love, about the feeling of it, about human history, and what it would mean to communicate across the cosmic distance to unknown intelligence, about the nature of consciousness, about being a mind in a body that had just been permanently changed by another person's existence. All of that thinking, in real time, was encoded in the record's neural data track. Her heartbeat was also recorded alongside it. She noted afterward that her heart was beating faster than usual because she had just fallen in love, and her body knew it before she had quite finished deciding with her mind. An accelerated heartbeat and the brainwaves of a person in the first hours of knowing they are in love, both encoded in the grooves of a gold-plated copper disc, currently moving through interstellar space at 17 kilometers per second, 25.6 billion kilometers, from the phone call that made them elevated. The music selected for the record came from 27 pieces across cultures and centuries. Johann Sebastian Bach appears 3 times. The Brandenburg Concerto No. 2 opens the record, which some people found excessive and others considered the minimum reasonable. Chuck Berry's Johnny B. Good made the journey because raw joy and electric guitar seemed like things worth introducing to the universe. Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless 1927 recording of slide guitar and humming, one of the most moved and moving pieces of music ever set down on record, expressing something about loneliness and endurance and beauty that language would only diminish, was included because Sagan described it as the piece of music on the record that most honestly expressed the loneliness of the human condition. A Navajo night chant, Georgian polyphony, a Peruvian wedding song, a raga by Kesarbai Kerkar. The music does not agree on anything except that it is music, and in that agreement it contains more about humanity than any argument could. 115 images were encoded in analog format, human anatomy, mathematical definitions, the structure of DNA, the solar system with its planets, a nursing mother, a man eating from a bowl, children playing a traffic jam. The record does not pretend the traffic jam doesn't exist. Spoken greetings in 55 languages, including Akkadian, last spoken by living people more than 2,000 years ago, and a child's voice in English saying, "Hello from the children of planet Earth." Jimmy Carter wrote a message for the record's cover. "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Jimmy Carter died on December 29, 2024, at age 100. He was alive for 47 years of a mission he helped send, a mission that by the time of his death had already crossed into interstellar space and was carrying his words through the dark. The record itself is gold-plated copper. The cover is gold-plated aluminum. Estimates of how long it will survive in the cold, radiation-thinned environment of interstellar space, protected from the sun's degrading radiation by its own immense distance, run to hundreds of millions of years, possibly a billion. The sun has approximately 5 billion years of hydrogen fuel remaining before it begins expanding into its red giant phase. Earth's oceans are expected to begin evaporating within about 1 billion years as the sun gradually brightens. Long before any of that, Voyager will be far beyond the reach of any such solar events, carrying Druyan's heartbeat and Bach, and a child's hello and Jimmy Carter's hope in the dark, long after every other human-made object has returned to the elements it was made from. To understand why Voyager still hasn't left the solar system after 49 years, you need a picture of what the solar system actually is. Not the schoolroom picture with 8 planets in neat rings, color-coded and labeled and ending at Pluto. That picture ends too soon. The real solar system is layered and dynamic and extends far beyond anything in that image. It has several edges, depending on how you define edge. And Voyager has crossed some of them and is still approaching others. The sun is constantly losing mass into space. Every second it emits a stream of charged particles, protons, electrons, helium nuclei, moving outward in all directions simultaneously at 400 to 800 kilometers per second. This is the solar wind. It has been blowing continuously for 4.5 billion years. It never stops. It flows outward, growing thinner, with distance but never disappearing, creating an enormous invisible bubble around the entire solar system. This bubble, the heliosphere, extends well beyond all the planets, well beyond the Kuiper Belt with its frozen worlds, out to a boundary called the heliopause, where the solar wind's pressure is finally balanced by the pressure of the interstellar medium pushing inward from outside. Inside the heliopause is the sun's domain. Outside is interstellar space. The heliosphere is layered internally. Moving outward from the sun, the solar wind flows freely and supersonically until it hits the termination shock, the boundary where it abruptly slows, decelerating from supersonic to subsonic speeds because the interstellar medium's counterpressure is finally great enough to push back. Beyond the termination shock is the heliosheath, a turbulent zone where the slowed solar wind continues outward, churned and pressurized by its collision with what lies outside. At the far edge of the heliosheath is the heliopause itself, and the heliosphere serves a function you benefit from every day. Galactic cosmic rays, high-energy particles produced by supernovae and other violent events across the galaxy, stream through interstellar space at nearly the speed of light. The heliosphere's magnetic field deflects many of them before they reach the inner solar system. The sun is not just a source of light and heat. It is a shield, and the heliosphere is the shape of that shield, surrounding us, holding back the galactic radiation that would otherwise reach us unfiltered. Let the weight of this find you properly. The room you're in right now is inside the heliosphere, inside the sun's magnetic bubble, inside a shield 4.5 billion years old. Outside that shield is the raw interstellar medium, denser in certain ions, colder in certain ways, carrying the unfiltered cosmic rays of the galaxy. And somewhere out there in that medium, on the other side of the shield, two small human-made objects are moving in the dark, measuring what it's like, sending the data home at 23 watts, still talking. Let your body go heavier now. The mattress holds you completely. You don't have to hold yourself up. Your breathing can slow all the way down to whatever it naturally wants to be when nothing is asked of it. The heliosphere is where it always is. Both Voyager spacecraft are moving. You can be still. This is the right arrangement. That something we built goes outward into the dark while you rest inside the warmth of the only home we've ever known. Let that be enough for a moment. Let it be more than enough. Voyager 1 crossed the termination shock in December 2004 at approximately 94 astronomical units from the Sun. This was a moment 32 years in the making for Ed Stone, the project scientist for the entire Voyager program. Stone had taken on the role in 1972, before the spacecraft existed in its final form, when the mission was still being argued for and funded and built. He was there for the construction, the launches, the Jupiter encounters with their volcanoes and hints of oceans, the Saturn encounters with their impossible ring complexity. He was there through the long, quiet decades when the spacecraft moved outward through uncharted territory, measuring the gradual change in conditions as the sun's influence grew fainter. 32 years of waiting for the termination shock, and then it arrived. The crossing was not immediately clean. In 2002 and 2003, instrument readings suggested Voyager 1 might have crossed the termination shock, but then the signatures reversed. The boundary had moved outward, pushed by an increase in solar wind activity during a period of heightened solar output. The heliosphere breathed slightly with the sun's 11-year activity cycle. The termination shock is not a fixed line, but a dynamic surface. By December 2004, the crossings was unambiguous. The plasma data changed. The magnetic field data changed. The particle data changed. The solar wind had slowed from supersonic to subsonic. The heliosheath had begun. Stone was still there. He continued. Voyager 1 crossed the heliopause in August 2012, 40 years after he started. Stone was there, part of the team that confirmed the crossing through the plasma oscillation measurements, that revised the magnetic field models when the data came back different from predictions, that worked through what it meant that humanity had, for the first time, sent an object outside the bubble of the sun's influence. He continued through Voyager 2's heliopause crossing in November 2018, 46 years into his tenure. He retired from the Voyager project in 2022, 50 years after he began. During those 50 years, he watched 3 separate historic boundaries crossed by spacecraft he had helped oversee since before they launched. He told interviewers late in his career that the heliosphere had turned out to be far stranger than anyone predicted when the project started. He said it in the tone of someone who considered that the best possible outcome, that science had revised itself repeatedly in contact with the actual universe. 50 years, 3 boundaries, 1 project scientist. Voyager 2 crossed the termination shock in August 2007 at approximately 84 astronomical units, a different distance than Voyager 1's 94 astronomical units from a different direction. The heliosphere is not a perfect sphere. 2 data points in 2 directions are already more information than 1, and both data points were needed. August 25, 2012. That is the date Voyager 1 crossed the heliopause. The confirmation took time because the plasma wave instrument, which provided the definitive measurement, had been damaged years earlier and could not take direct density readings. The team had to wait for a solar energetic particle event, a burst from the sun that would cause the surrounding plasma to oscillate at a frequency that revealed its density. That event came in April 2013. The plasma oscillated. The frequency revealed the density, 40 times higher than in the heliosheath. 40 times. Because the heliosheath had been swept by the solar wind for billions of years, thinned and processed, while the interstellar medium outside was raw and unprocessed galactic material. The science paper confirming the crossing was published in September 2013. The most significant boundary in the history of human spaceflight was confirmed retroactively from an echo of a solar flare in plasma that nobody on Earth had touched or would ever touch. The magnetic field at the heliopause was wrong, oriented differently than models predicted. This was not a minor discrepancy. It required genuine revision of the models of the local interstellar magnetic field. And it was welcome, because science that revises itself is science working. Voyager 2's heliopause crossing in November 2018 at 119 astronomical units versus Voyager 1's 121 astronomical units in a different direction added the second data point. The heliosphere is not perfectly symmetrical. Both crossings showed the same result. Galactic cosmic ray counts jumped dramatically on the interstellar side. The shield works, and it stops working exactly at the heliopause. There is something just outside the heliopause that most accounts of Voyager don't describe. And I want to linger there for a moment, because the image is one I find genuinely beautiful. Right at the boundary between the heliosphere and the interstellar medium, where the solar wind pressure and the interstellar medium pressure reach their equilibrium, there is a phenomenon called the hydrogen wall. Interstellar hydrogen, the most abundant element in the universe, present at roughly 1 atom per cubic centimeter in the space between stars, doesn't flow freely right up to the heliopause boundary. As it approaches, it is compressed and slowed by the magnetic and thermal pressure building at the boundary, piling up in a thickened layer on the outside of the heliopause. A wall of hydrogen, denser than the interstellar medium further out, denser than the heliosheath within, caught between two regimes and compressed at their meeting point. The hydrogen wall was first detected not by Voyager, but by the Hubble Space Telescope in 1996, using ultraviolet spectroscopy, observing the way the wall absorbs specific wavelengths of light from nearby stars, and comparing that absorption pattern to what you'd expect from a simpler model. The signature of a compressed hydrogen layer was unmistakably there. Other stellar systems appear to have their own hydrogen walls too, suggesting this is a universal feature of stars, with significant solar winds moving through the interstellar medium. Every star with a heliosphere has this wall, where its influence meets the galaxies. Voyager has now passed through ours. It is on the other side of the compression zone, in the open interstellar medium, where the hydrogen is sparse and undisturbed. The wall was the last feature of the solar system it crossed before entering truly open interstellar space. The interstellar medium Voyager is moving through right now is not generic or uniform. It has its own geography. Voyager is currently in a specific region called the Local Interstellar Cloud, sometimes known as the local fluff. A name I find captures its quality better than the formal designation. The local fluff is a warm, partially ionized region of hydrogen and helium approximately 30 light-years across. The Sun has been moving through this cloud for roughly 100,000 years. By interstellar standards, it is a relatively soft, warm neighborhood. The temperature of the gas here is around 6,000 Kelvin, which sounds hot, but in terms of particle energy, is quite mild compared to the much hotter gas in the surrounding region called the local bubble. The local bubble is a roughly spherical region, approximately 300 light-years across, that surrounds our solar neighborhood. It was carved out by a series of supernovae that occurred between 10 and 20 million years ago. Explosions so powerful, they expelled most of the interstellar material from a large region and left behind a cavity filled with hot, thin, low-density gas We live inside that cavity. The local fluff is a smaller, denser cloud drifting through it, and within the next 10,000 to 20,000 years, models suggest the sun may exit the local fluff and enter one of the cooler, denser clouds at its edges. When that happens, the denser external medium will push harder against the solar wind, compressing the heliosphere inward, potentially shrinking it significantly. A smaller heliosphere means more galactic cosmic rays penetrating to the inner solar system. On geological timescales, changes in the character of the interstellar medium the sun passes through may have influenced Earth's long-term climate. We are travelers, and the neighborhoods through which we travel are not constant. What Voyager is measuring out there, the hydrogen density, the magnetic field orientation, the plasma properties of the local fluff, is data that no instrument has ever collected from that vantage. The local fluff has been studied remotely, from inside the heliosphere, using telescopes and spectroscopy. But Voyager is in it, moving through it, feeling it directly, sending back readings from inside. There has never been an instrument in the interstellar medium before. Everything Voyager measures there is, in the most literal possible sense, unprecedented. In November 2023, Voyager 1 started sending nonsense, not silence, data. The transmitter was working. The spacecraft was operating at some functional level. But the flight data system, one of 3 onboard computers, responsible for collecting, formatting, and packaging all science instrument data for transmission, was producing output that made no sense. Garbled packets, corrupted formatting. The engineering team at JPL could tell Voyager was alive and transmitting, but they could not read what it was saying. It was as if someone familiar called you on the phone. You could hear that they were speaking, but the words had stopped being words. The flight data system runs assembly language code written in the early 1970s for hardware that hasn't been manufactured in decades. Many of the engineers who originally wrote and intimately understood that code have retired. Some have died. The institutional knowledge of how to think in terms of 1970s computer architecture, registers, memory addresses, machine-level operations, hardware-specific instruction sets, has been thinning for years. The team that manages Voyager today has absorbed what they could through years of careful work on the mission. But facing a new and uncharted failure mode in old code, across a communication link with a 48-hour round trip, is one of the most extreme engineering challenges the space program has faced. There is no parallel to this kind of problem on Earth, where you can walk over to the hardware and look at it, or reload the software, or replace the component, or simply try the next thing in a sequence and know the answer in minutes. Every diagnostic step was a commitment of 2 days minimum. Send a command, wait 23 hours and 40 minutes for it to arrive at Voyager. Wait for the spacecraft's response. Another 23 hours and 40 minutes for it to return. A single exchange takes nearly 48 hours. Iterating through possibilities at that rate requires a patience that is genuinely unusual. Not the patience of waiting for something to happen. The patience of waiting to find out whether something you already did 2 days ago worked or didn't. This specific quality of deferred feedback stretched across 2 days of silence between each action and its consequence, is something the Voyager team has been living with for decades. It becomes over time a different relationship with uncertainty than most engineering work demands. In January 2024, the team sent commands for the flight data system to perform a complete memory dump, to transmit the contents of every chip, every register, every memory location back to Earth. The dump arrived. Engineers examined it over weeks, and eventually they found it. A single faulty memory chip within the flight data system was no longer reliably storing data written to it. The chip had developed a fault, not unreasonable for hardware in the radiation environment of interstellar space for 46 years. The code that depended on that section of memory was producing corrupted output because the memory it was writing to and reading from was no longer trustworthy. The solution required working within constraints so tight that the engineering itself became a kind of art. They couldn't replace the chip. It is 25 billion kilometers away. They couldn't reload from a clean backup. No such thing exists for Voyager. What they could do was identify the exact lines of code stored in the faulty memory chip and relocate those lines carefully, one section at a time, with full verification at each step, to other sections of the flight data system's memory that were still reliable. The memory was not designed with relocation in mind. The code was 46 years old and written for specific addresses. Every memory reference in the moved code had to be updated. Every interaction with the rest of the system had to be verified. All of this done in slow motion through a 48-hour communication round trip, with hardware already running on borrowed time. On April 20, 2024, Voyager 1 resumed sending coherent science data for the first time in 5 months. The readings were real. The instruments were working. The data was readable. Something had been fixed from 25 billion kilometers away. Using assembly language written before most of the engineers doing the fixing were born, through a communication link so slow that every attempt required 2 days of silence before you learned its result. The response at JPL, by every account, was exactly what you'd expect when a team that has worked on something for decades, some of them for their entire professional careers, watches it come back to life. Patient, precise, caring work across an impossible distance had succeeded. Here is why Voyager still hasn't left the solar system. The solar system, properly understood, extends far beyond the heliopause. It extends, gravitationally, by the sun's reach, to a structure called the Oort Cloud, which begins at approximately 2,000 astronomical units from the sun and extends, by current estimates, to 100,000 astronomical units or beyond. At its outer edge, the Oort Cloud reaches 1 to 2 light-years from the sun, roughly a quarter to halfway to Alpha Centauri. Voyager 1, at 171 astronomical units, has not yet reached the inner edge of the Oort Cloud. It will reach that edge in approximately 500 years. Around the year 2537, it will pass through the full cloud over the following 14,000 years. And then, finally, it will be in the true space between stars. The idea was proposed independently by 2 people at different times. Ernst Opik, an Estonian astronomer, published the argument in 1932. Long-period comets must originate from a distant reservoir of icy bodies at the solar system's gravitational edge, because their orbital parameters cannot be explained by any closer source. His paper was correct and was largely set aside. Jan Oort, a Dutch astronomer, arrived at similar conclusions through careful comet orbital analysis in 1950, published a landmark paper, and the structure was named for him. Many astronomers now say Oort Cloud, and I think they're right about that. Ernst Opic got there first. He deserves the hyphen. What makes the Oort Cloud genuinely strange is this: we have never directly observed a single object in it, not one. Everything we know about it, its existence, its size, the number of objects it contains, its spherical geometry, is inferred from the behavior of comets that fall inward toward the Sun. When a comet has an orbital period of tens of thousands of years, astronomers calculate backward along its orbit to determine where it came from. When many such back-traced orbits point to the same region of space at the same distance range, you infer a population there. The Oort Cloud is real, we are nearly certain. But we are certain of it the way you might be certain of something you can prove must exist without having ever seen it. The argument is sound. The thing itself remains unseen. The Oort Cloud is thought to contain 1 to 2 trillion objects larger than 1 kilometer across. 1 to 2 trillion, not million, trillion. The leftover material from the solar system's formation, flung outward by gravitational interactions with the giant planets during the chaotic first billion years when the solar system's configuration was still being negotiated. They orbit the Sun so slowly at such vast distances that a single revolution takes from tens of thousands to millions of years. And the Oort Cloud is not a disk. It is a sphere, a complete shell in all directions around the solar system. Above and below and surrounding, 1 trillion sleeping bodies orbiting in the dark that has not changed since they arrived there. What disturbs them occasionally is the passage of nearby stars. As the Sun moves through the galaxy over millions of years, other stellar systems sometimes come within a few light years, close enough that their gravity nudges some outer Oort Cloud objects out of their ancient equilibrium. Some of those nudged bodies fall inward, pulled gradually by the Sun's gravity over thousands of years, and eventually become the great comets. Brilliant, tailed visitors moving through the inner solar system for the first time in their existence, or their first time in 10,000 years. Comet Hale-Bopp, which lit up the night sky in 1997, was an Oort Cloud visitor. Its last close approach was about 4,200 years ago. Its next will be roughly 500 years from now. Comet Hyakutake, which appeared the year before and was briefly the brightest comet in decades, also traced to the outer solar system. Every great comet that human beings have looked up at in wonder and named and feared and celebrated is an Oort Cloud traveler, a 4-billion-year-old body making its first or rare pass through the warm inner solar system before returning to the cold for another few thousand years of silence. Voyager 1 will enter the inner Oort Cloud around the year 2537, 511 years from now. By then it will have been silent for centuries, its power exhausted, its transmitters cold, its instruments dark. But the object itself will continue moving. The golden record will continue. For 14,000 years, Voyager 1 will drift through the region where the trillion sleeping bodies orbit, the region that launched every great comet any human being has ever seen, carrying Druyan's heartbeat and Bach and Jimmy Carter's message in complete silence among the comets. In March 2004, astronomers Michael Brown, Chad Trujillo, and David Rabinowitz discovered a small world at the inner edge of the Oort Cloud region, or possibly the far outer Kuiper belt. The boundary is a matter of definition. They named it Sedna, after the Inuit sea goddess who lives at the bottom of the Arctic Ocean. Sedna's orbit, perihelion of approximately 76 astronomical units, aphelion of roughly 937 astronomical units, orbital period of about 11,400 years. It takes 11,400 years for Sedna to complete one trip around the Sun. Nothing in the known solar system should have placed it there. Neptune's gravity at 76 astronomical is negligible, and no known mechanism explains the shape of Sedna's orbit. Here is what stays with me about Sedna. We found it near its closest approach. Right now, in the span of an 11,400-year orbit, Sedna is at the relatively close, relatively bright end of its journey, briefly near enough for our best telescopes to detect. Within a few centuries, it will have retreated to distances where no current telescope could see it at all. It won't be this close again for 11,400 years. We barely caught it. A few decades in either direction, and it would have been invisible. An unknown world orbiting in the dark, its existence unsuspected. The mystery it represents unasked. A second Sedna-class object, 2012 VP-113, nicknamed Biden by its discoverers Chad Trujillo and Scott Shepard and announced in 2014, has a similar orbital shape at similar distances. Two objects with similar, inexplicable orbits in the same region. When two independent things agree on something improbable, it stops being coincidence. In January 2016, astronomers Konstantin Batygin and Mike Brown at Caltech published a paper proposing that the orbital clustering of several distant Kuiper belt objects was best explained by the gravitational influence of a large, undiscovered planet in the outer solar system, 5 to 10 Earth masses, orbiting at hundreds of AUU, with a period of 10,000 to 20,000 years. They called it Planet 9. It has not been found. It has not been ruled out. The Vera C. Rubin Observatory in Chile recently completed and now conducting its decade-long legacy survey of space and time with the largest digital camera ever built for astronomy, is expected to either find Planet 9 or definitively rule it out within a few years. Mike Brown also happens to be the person most responsible for Pluto's demotion. His discovery of Eris, a Kuiper belt object comparable in size to Pluto, forced astronomers to either count Eris as a planet and eventually many similar objects, or revise the definition of planet to exclude both. They chose the revision. Brown considers this his greatest achievement. He got Pluto demoted, and he might have found the actual 9th planet, which has been hiding at hundreds of AU for 4.5 billion years while everything else in the solar system was happening. If Planet 9 exists, it was there through all of it, orbiting in the dark, undetected, while the Earth formed and the oceans filled and life began, and all of recorded human history unfolded, and Voyager launched and flew for 49 years. One planet 9 orbit encompasses all of that. Easily, let the outer solar system hold you now, right now, in every direction above you. Since the Oort Cloud is a sphere surrounding us in all directions, there is a shell of approximately 1 trillion objects orbiting the Sun on timescales of millions of years. They have been there since before the Earth existed. They are not waiting or anticipating. They are simply orbiting, as they have always orbited, in the cold and the dark and the silence. And in 500 years, one small human-made object will enter that shell and move through it for 14,000 years, in silence among the sleeping bodies carrying its cargo. Your breathing has slowed. That's the right direction. The day's concerns are unchanged. Nothing about them has shifted in the last hour, but the distance between you and them has grown in the way that large perspective creates genuine distance from small, immediate things. You don't have to hold the Oort Cloud in organized memory. Let it be true in the background somewhere while the foreground grows soft and quiet. The trillion objects orbit. Voyager moves. You can rest. The shape of the heliosphere is not what physicists thought for most of the Voyager mission's life. The standard picture, for decades, was a comet shape. The leading edge compressed by the interstellar medium pushing against the Sun's direction of travel, and the trailing side extended into a long tail like a cosmic windsock or a teardrop blown backward. This made physical sense, and most models agreed on it, and it was wrong, or at least substantially incomplete. IBEX, the Interstellar Boundary Explorer, launched in 2008, began to disassemble the picture. IBEX orbits Earth and detects energetic neutral atoms streaming back from the heliospheric boundary, using them to map the boundary's properties without traveling to it. In 2009, IBEX found a ribbon of intense energetic neutral atom emission running perpendicular to the local interstellar magnetic field. Something no model had predicted. A ribbon, completely new, requiring years of theoretical work to even begin to explain, still debated. In 2012, IBEX found no bow shock. Earlier models had predicted that the Sun, moving through the interstellar medium, would produce a supersonic shockwave ahead of the heliosphere, like the shockwave ahead of a supersonic aircraft. IBEX found no evidence of one. The heliosphere is not moving through the local fluff fast enough, relative to the local conditions, to produce a classical bow shock. A 2017 paper suggested the heliosphere might be more accurately described as a croissant shape, or a crescent with two trailing lobes, rather than a long-tailed comet. IMAP, the Interstellar Mapping and Acceleration Probe, launched in 2025 as IBEX's successor, is designed to map the boundary at higher resolution and should clarify the question within a few years. What is already clear is the lesson the Voyager program has been teaching since 1977. Whatever you thought you knew about the edge, wait until you get there, and then revise. One more thing before the ending. Voyager 1 transmits at a frequency of approximately 2.3 GHz, the S-band in radio engineering terms. That frequency is close to the 2.4 GHz band used by Wi-Fi routers and some cordless phones. The signal from Voyager 1, crossing 25.6 billion kilometers, arrives at the receiving dish at a frequency not very different from what your home router sends across the room. The physics of the electromagnetic wave is the same. What differs is the distance traveled, the power at the source, and the signal strength at arrival. A router's signal fills a house with useful data. Voyager's signal, by the time it has crossed 25 billion kilometers, carries less energy than a quadrillionth of a watt. To detect it requires a dish 70 meters across, a receiver cooled almost to absolute zero, and electronics so quiet that the signal from interstellar space can be pulled from the noise, and every day it works. There is something about that comparison. The same frequency, incomprehensibly different scales, that captures something essential about Voyager in miniature. The technology is not exotic. The physics is the same physics running through your walls right now. The only thing that changed is the distance, and the distance changed everything. When Voyager 1's power finally gives out, probably before 2030, as the RTG output continues declining below the threshold needed to keep any instrument functional, it will go dark. The transmitter will stop. The signal that has crossed 25 billion kilometers for nearly 50 years will end. And after that, the object continues, moving, not transmitting, not heard, but moving at 17 kilometers per second, unchanged from the speed it has always had, because there is nothing in the space between stars to slow it. It will move into the Oort Cloud in 2537. It will move through the Oort Cloud for 14,000 years. It will exit the Oort Cloud in silence, some 15,000 years from now, and enter the open interstellar space between stellar systems. And then it will drift, following the motion of the Sun through the galaxy, for longer than the Sun has left to live. The golden record will not degrade on any of those timescales. Gold-plated copper in the cold and radiation-thinned environment of deep interstellar space has been estimated to survive in usable condition for hundreds of millions of years, possibly a billion. The Sun will become a red giant in approximately 5 billion years and consume the inner planets. Earth's oceans will begin evaporating within about 1 billion years as the Sun brightens. Long before any of that, Voyager 1 will be tens of thousands of light years from wherever Earth used to be, drifting through a galaxy that will have changed in ways we cannot fully model, still carrying Druyan's accelerated heartbeat, still carrying blind Willie Johnson's wordless grief and beauty, still carrying a child's hello and a president's hope, long after everything else we have made has returned to the elements it was formed from. In approximately 40,000 years, Voyager 1 will make its closest approach to another star, a red dwarf called Gliese 445 in the constellation Camelopardalis. The star is approaching our solar system, so both objects are moving toward the encounter. The closest approach will be within 7 light-years, not close enough for any dramatic event, not close enough to be captured gravitationally, just close enough that if Gliese 445 has planets with observers capable of watching the sky carefully, something will cross through the outer gravitational reaches of their system. A dark, silent object, moving at a speed suggesting purpose, carrying a disk that, if recovered and understood, would tell them where it came from, and who sent it, and a little about what we cared about in the year 1977. Voyager 2 will pass within 4.3 light-years of Sirius. The brightest star in Earth's night sky, the star ancient Egyptians tracked to predict the flooding of the Nile. The star woven through more human sky mythology than perhaps any other, in approximately 296,000 years, 300,000 years, a time that contains all of recorded human histories 150 times over. Carrying Chuck Berry and Bach and a Navajo night chant and a human heartbeat elevated by love, still encoded in its grooves, into the neighborhood of the brightest star in our sky. These are not projections. They are calculated trajectories. Voyager is going there. The signal that left Voyager 1 before you started listening tonight is close to Earth now. Closer by however many hours have passed since you began. By the time you've been asleep for a few hours, it will have reached the dish at Goldstone, or Canberra, or Cebreros, whichever antenna of the Deep Space Network was aimed at the right quadrant of the sky tonight. It will be received. The faint fractional watt whisper will be amplified and decoded and turned into numbers, and the numbers into readings, and the readings into another entry in an archive that has been accumulating for 49 years. Measurements of what interstellar space is like. Right now, at a specific location 25.6 billion kilometers from the only home any of us has ever known. And Voyager will already have sent the next signal, and the next. It transmits continuously, because the people who built it believed in the unbroken record, in the importance of sending back everything, for as long as possible, without stopping. That principle has held for 49 years. It will hold until the power finally fails. And after the power fails, the object will hold to its own version of the same principle, continuing without being able to say so, carrying without being able to report what it carries, moving without any instrument left to measure the moving. I want to leave you with what I think the Voyager mission actually is, at its deepest level. Not an engineering achievement, though it is one, extraordinary and unrepeated. Not a scientific program, though it has produced science that could not have been produced any other way. I think Voyager is the most honest statement our species has ever made about what it is. In 1977, a species that had existed in roughly its current form for a few 100,000 years, that had been writing things down for about 5,000, that had understood the heliosphere for a handful of decades, built 2 machines on 69 kilobytes of memory and aimed them at the edge of the solar system, and put on them a record of the most important things it knew how to feel and express and be, and sent them. Not because it was practical, not because there was a return on the investment, because the window was there, and because something in us, when given a window and the means to go through it, goes. The answer to the question, what are we, is currently moving through the local fluff at 17 kilometers per second. The answer is Bach and Anne Druyan's heartbeat, and the sound of a mother's first words to her child, and Blind Willie Johnson's grief hymn on a slide guitar, and the image of a nursing mother, and a child saying hello, and a president hoping we survive our time, moving through the hydrogen wall and into the open interstellar medium toward the trillion sleeping bodies of the Oort Cloud, toward a red dwarf star 40,000 years ahead, toward Sirius in 300,000, toward a billion years of silence that will outlast everything else we have ever made. We are still listening Tonight, the Deep Space Network antennas are cold and aimed and waiting. The signal is coming. It crosses the dark the way all signals do, without knowing whether it will arrive, without knowing whether anything is listening, carrying what it carries regardless. It has been doing this for 49 years. It will do it for a few more years, and then continue without doing it, and carry its cargo into the silence that will eventually outlast everything. You can rest now. Voyager is awake so that you don't have to be. It went to the termination shock and through it, to the heliopause and through it, through the hydrogen wall and into the local fluff, and out into the open interstellar medium. It reported back every step of the way, and we listened. And the listening changed something in us, made us more humble, more certain that the universe is stranger and richer than any model we had prepared for it. Ed Stone spent 50 years on that listening. Anne Druyan put her heartbeat into the message. Linda Morabito stopped and asked, "What is that?" and found the first volcano beyond Earth. Carl Sagan lobbied for 3 years to turn a camera backward and photograph a pale blue dot that still, decades later, corrects something in the chest when you look at it. The heliosphere is where it always is. The Oort Cloud is patient in the dark. The local fluff drifts past the sun on its 100,000-year passage. The signal from Voyager 1 is almost home. By morning, it will have arrived. And you are here, warm, still, breathing, on the only world anyone you have ever known has ever called home. Inside the heliosphere, inside the local bubble, inside the Milky Way, inside a universe that makes room for sleeping, as naturally as it makes room for everything else. The spacecraft is moving, you can be still. Sleep well.